Hey guys, in our today's screencast I want to talk about draw. Draw is the entry point to the OpenCascade library, and actually it's pretty important to understand what this draw application exists, and then why should you care about draw, what is the function of draw. So basically there are several use cases you can find for draw, like you can find several use cases where this application can be useful, and as I said, it's sort of an entry point to the whole library, so you can try out different things of the library, you can try out different API functions of OpenCascade in there. But that's not the only use case actually, because also if you are going to prepare a bug report to the official bug tracker of OpenCascade, you are supposed to use draw. You are supposed to prepare your reproducer script in draw and then to attach it to your bug report. Then also draw can be useful for batch processing, like if you have some job to be done in background, if you want to run something on a server, for example, on your backend, you can also go for draw. And the final use case, the fourth use case for draw, is non-regression testing. As long as draw allows to run different scripts in a batch process, you can also benefit from it. And also draw is supplemented with a reporting functionality, like you can prepare first of all your test cases, you can prepare your test scripts, then you can run them all in a batch process, and then draw will end up generating HTML layout, HTML report with all the tests results. And here you can also benefit from the off-screen rendering functionality of OpenCascade, and you can supplement your non-regression testing report with some images with screenshots of your models, and this way to produce a nice report which you can use for daily development based on OpenCascade, especially if you are developing some CAD processing algorithms. So let's get started. Here in my installation folder I am going to run this script which is drawbot, and here we go. So we get this TCL prompt and also this tiny TK-based UI, this TK-based widget over here. It's not that useful, and the only thing which I want to show you right here is these samples. If you go to this view sample section, you will see this panel which is pre-populated with different TCL scripts which you might want to try out, like for example this milling cutter. You can just copy the blocks of TCL code from here and paste it to the TCL console on the right, or alternatively you can just hit this run sample button. It will do this modeling job in background, and it will show you the result of modeling, like this scene here. So here you can get insight on what OpenCascade can do for you without running any MFC samples or Qt-based samples. So it's pretty straightforward how you can navigate over the available set of modeling, and not only modeling commands actually. But let's close it for now, and I'm not going to return to this samples panel or to any other TK widgets of draw in the future, so let's close it and forget about it for now. So okay, so let's see what we can do with draw. Basically you always start from loading all the plugins, all the modules of OpenCascade library right here in draw. You can do that by typing this pload all, which is going to load all the modules of OpenCascade, or alternatively you can also load a specific module, like you can load only visualization if you want. You can load, for example, only modeling plugins, like this. But in most of the cases you just pload all and you are done. So let's see what we can do. We will start with creating a box shape. You give it a name. It's going to be a solid object with dimensions like 1, 1, 1. So let's create it, and then we can ask what is A. And A is solid object, and it has its own orientation, which is forward, and there are some other additional flags. If we want to visualize it, we can go like Axo. It will open up this axonometric view. You see that I have some other objects in there. I have this mill part there because it was constructed by a sample. So what I can do, I can clear everything, and then I can show only or display only my box, which is A, and then I fit the scene so that I can have it here. So the color codes here in this viewer are not random, like yellow color means that the corresponding edge is shared. It means that this curve, this straight curve segment here, is shared by two faces. And also you see these blue lines over here. These are just isoparametric lines of the corresponding host surfaces for my faces. Like I have all my faces planar. So what else can I do? Of course I can interactively, so to speak, navigate my scene. I can move it down or up using D and U keywords. Right and left are also available shortcuts. That's not very fun because it's not really interactive, it's sort of keyboard driven. If you want to have some OpenGl-based viewer instead, you go like vinit, which stands for visualization initialization, and vdisplay A. And here we go, we have, if I press F button over here, I have my scene fit available viewport, and then I can rotate the shape, and if I press Ctrl plus S, I have it in shading, and if I press Ctrl plus W, I have it in wireframe mode. This viewer is nice for if you want to interactively navigate your scene, but this axonometric viewer, which is a simplistic viewer of OpenCascade, it's still useful because, you know, it can visualize different anomalies, different defects of your shape, like if you have some, I don't know, some untrimmed face, or if you have some tolerance issue or some missing boundary representation entities, then it's easier to see all those defects of your shape here in axonometric view, because this viewer here, this OpenGl-based viewer, it relies on facetization, it relies on triangulation, and it means basically that triangulation algorithm has to be called before you can render something on a scene. And this algorithm itself is not very simple thing, it's a sort of very sophisticated algorithm, which can fail if you have some non-perfect geometry. So if you have some dirty geometry, then you might want to check your geometry using this simplistic axonometric viewer. This is one thing I want to draw your attention to. Then what we can also see here is, for example, this nbshapes command, and we can give it a name of our solid, and it will print the summary. It will print the summary of what do we have inside our shape. As expected, for a box shape, we are going to have like 8 vertices, 1, 2, 3, 4, and 4 on the bottom. Then we have 12 edges and 6 wires and 6 faces. Wire is a contour of a face, like each face is basically an infinite plane which is trimmed by 4 edges composed in a one contour. And this is what we see here, like we have 6 contours or 6 wires. Then all the faces are grouped to the shell object, and this shell is included into a solid object. So finally we have this solid, and in total we have 34 shapes here. So another useful thing of this draw console, why it truly serves as a prototyping workbench, is imagine that you manage to find the command which you want to use in C++, then how would you know how it is implemented? So basically, if I am interested in something like box, if I want to know how this box command is implemented, then I can go like getSource and give it a name of the command which I am looking for. So here you see the path like src, breptest, primitive command. So if I go back to my file manager over here in src, actually not here because it's installation folder, I need to find my folder with the sources of OpenCascade. There I have this package which is a breptest. I'm looking for this breptest primitive command, so this thing here. And here I can type, I can search for this box command. I have this command over here, I have this help hint, so it's going to appear if I run it without any arguments, or actually it's going to appear if I type it like help box. Yeah, this is much better, yeah, than standard domain error. And you see that what it prints is exactly these lines which I have here in the implementation. And when we have some magic macro over here which associates this command with this box command with the file, and this is actually what we get when we type getSource. The real implementation of this box command you can find by this pointer here. It's a function pointer, and then we have a group. This is basically just a hint, just a name of the corresponding group in TCL. Like all commands in TCL, they are kind of grouped, but this is something which we are not going to use ever. So let's just proceed with this function pointer over here. It's a function named box. So let's try to find one. So I'm going to make case sensitive search for the whole word, and you see that it's a first function. So what it does, we have some processing for our input arguments which we do not care of that much, and the useful code is located down below. You can see it as a brep prim API makebox, a function which we already used in one of the earlier exercises when we got started with OpenCascade from Visual Studio. So it's pretty powerful trick, I'd say. When you are familiar with DCL commands, you could easily navigate through the source file and find the implementation in there. But let's finally finish our boxy exercise and try to do something more exciting, because it really starts to be boring. Alright, so let's come back to Draw and try to do something useful. So I'm going to run it right now, again, and let's start with loading all the plugins we have. And I'm also going to open up like a top view. It's actually the same axonometric view, but here we look at our modeling scene from the top. Like you see what we have our X and Y axis, and we also have the Z axis which points towards us. So let's create a few vertices actually. So we need to do something like vertex. When we give it a name, let it be vertex 1, and let's give it a triple of coordinates, and I want to put my vertex in the origin point of my scene. So you see, vertex is here, and now I'm going to add 3 more vertices. So let me create vertex like 2, and I'm going to give it new coordinates. Then I can create another vertex 3 like this, and vertex number 4 coming back to x value equal to 0. So here we go, and now I can fit my scene, and I have all my vertices in the corners. And maybe I can also change the position of my vertex, so just to make it less, less simple. So let me go back to vertex number 3, and I'm going to change its coordinates to something like 5 and 5, for example. Or it's actually not that good, so let me do something like 7, 5, or 7, I don't know, 7, 8. So yeah, this is going to be a bit trickier for the modeler. And now I'm going to create edges. So let's do that. And for that I can use a command which is edge. And if I'm not sure how to run it, I can always go like help edge. And you see what I'm supposed to give it a name, like let it be edge 1 and vertex 1 and vertex 2. So here we go. And you see what happened internally. OpenCascade constructed a straight segment passing through these 2 vertices, and actually it's an infinite line which was automatically trimmed by OpenCascade. So now I'm going to add 3 more edges, edge 2 like this, then 3, and finally I'm getting back to my origin point using edge number 4. So here we have our contour, but actually this is only visually a contour, because OpenCascade doesn't create any wire, any loop of those edges automatically, and we need to do this by ourselves. Like what we do, we create a wire. Again, I'm not sure how to run it, so I go like help wire, and now I'm supposed to give it a name, and I'm supposed to enumerate all the edges which are going to constitute my wire, like this. So now I have a wire, and now I can also check that I'm done successfully with that. So let's go like what is W, and now we have this wire. Okay, now let's make a face. To make a face I need to use a command like mkface. So you see that I'm supposed to give it a name like face name here, and then I also need to give it like a surface name, and so far I do not have any surface. So that is the right time to create a planar surface for our projection view. So I'm going to create a plane, and for a plane let me give it a name again, and now I need to specify its origin point. So let's put the origin like origin of our local coordinate system which is associated with our plane right into origin of our scene here. And I'm also supposed to give it direction, like I want my plane to be oriented towards us. So let me specify its normal vector, which is 0, 0, 1. Now I have a plane. And you see, if I fit my scene, that I have sort of infinite plane here. And now the trick is to trim this plane with a contour, and for that I'm going to use this mkface. So let's do that. I'm going to give it a name like F, surface name is P here, and you can also notice that the last argument in there is this name of our wire. So I need to pass W over here. And now I can check what is F. And F is a face, so I can display only this face and fit my scene. So here we go, you see that all edges become green. It means basically that all those edges are not shared. If you remember, the shared edges are rendered in yellow color. So now it's probably time to switch to the axonometric view to look at our modeling scene from a different perspective. Or I can also do something like MU4. It's going to open up 4 viewers from different positions. And if I fit it, then I see my scene from all the standard positions, from all the projection views like this. Now let's switch from this sketch to some solid primitive. For that I'm going to build up a prism. So here we go, you see that to build up a prism I need to give it a name, like let's call it a prism. And then what do we have here? We also have this base face, which is going to be our F. And then I also give it the direction of extrusion. So in the simple case I can go like 0, 0, 1. And also here this vector of extrusion, it's sort of a vector with a magnitude. So if I keep 1 here, it's not going to be the same as if I put 2 here, for example. So let's start with 1. And you see I've got my prism. You can also notice that all the edges become shared. This is something you can see from the color of those edges. And let me change it like 2, for example. Or I don't know, 3. Already here you can notice that TCL scripting is a way to do some parametric modeling with OpenCascade. Like imagine that I put all this code in TCL procedure and I sort of parameterize it. I declare the design parameters of my prism, like I can give those coordinates of vertices, and I can also use this height of the prism as my design parameters. And then in order to do some parametric modification of my shape, what I need to do, I need to call this procedure once again with different values. Actually it's going to rebuild the whole thing from scratch. It's not any sort of direct editing or direct modeling, but it's still extremely useful in many scenarios. So let me also try some different extrusion direction like this, and you see my prism is skewed now. Okay, so let's keep just one viewer. I'm going to do it like X and fit. And let's also switch to OpenGl viewer. So here we go, we have our prism object. And now let's see how I can do some, you know, more delicate modeling having this initial prism as a raw material. So let's say I want to put a fillet, like I want to blend this edge here. To do that I need to have some pointer to this edge, I need to have some address, some name of this edge, because I cannot easily use draw as a CAD system, for example, where you have different selection modes and all those things. So let's see how can I do this. For that I need to give this edge a name, and to do so, the first thing I'm going to do, I'm going to explode my prism onto the edges. And you see that I have 12 edges, just like I had 12 edges in the box. And if you are curious about this explode command, you can also go like help explode, and you will see the hint. Like you need to specify the type of a subshape you are going to explode your entity onto. Like if I want to explode my entity onto edges, I pass E here. I can also go for faces, wires, vertices, shells, solid, compounds and comp solids. I think CD is for comp solid. So now that I have those edges, actually I have them rendered right into the same viewer as distinct entities. So what I'm going to do now, I'm going to pick interactively this entity over here, and for that I can go like erase, and then I put dot here. Dot means interactive selection. Now draw invites me to interactively select some entity on the scene. So if I try to hit this entity, if I am not precise enough, it's going to erase the prism object itself, so I can repeat this experiment over here. Or I can even type dot twice, like I am supposed to pick 2 entities from the viewer. 1 and 2. And you see that I am done, I have prism 4 and prism 12. Those primitives are actually the edges, and I can double check this. If I go like whatis, then prism 4, you see it's an edge, and prism 12, it's also an edge. Here I'm not quite happy with the names of those entities because I want them to be like shorter, and let's rename them. To do that, I need to go like renamevar. Var stands for variable, and here I'm not quite sure what I'm supposed to do. Okay, here I need to give it the old name like prism 4, and I give it a new name like h4. And you see this entity appears again in the scene, and let me do the same for the 12h. So here we go. Now I have just better names for those entities. And now I'm going to do something like fillet. And you see now I am done, so I have this fillet over here, and I can also specify different radii for different edges, like I will blend edge number 12 with different radius, and here we go, we have our blended shape. Now if I want to communicate my shape to some external CAD package like SolidWorks or CATIA for example, I can export it to some open format like step, and here I'm going to use this step translator of OpenCascade, which is a pretty amazing thing. It's very robust and efficient, so let's benefit from it here, and for that I'm going to do a couple of checks before I go for this export routine. So first thing to check is that my shape is sound and perfect. For that I'm going to run this checkshape command, and here I type this res. I'm also not quite sure right now what is this res object, so let me check it again. What is res? Oh, I can also go like point here and interactively select this object on a scene. And you see that res is a shape, it's a compound, and that's kind of, kind of surprising, because I would expect it's a solid object. And if you say compound, then it's an indication that you have a sort of external container which might contain your solid, or it can also contain something like a set of faces, and this is not something I want to have, because a solid object is a more sound entity. A solid object puts some more restriction to your boundary elements, like you expect that you can compute a volume of your solid and all the faces of your solid are sort of properly oriented, like you have all the normals of all your faces pointing outward the solid object, the enclosed volume of the object. So let me go like explode this entity over here and see what is inside. So I have this res1, and finally I check what is res1, and finally I get my solid. So actually this compound was sort of, sort of artificial entity which I'm not going to use anymore. Okay, so now I'm sure that this solid object is correct. Like I have this output from the checkshape command, and what I am also going to check is the geometric tolerances which are associated with my brep entities. For that I go like tolerance res1, and here I have these tolerance values which are associated with all the boundary elements, with all the geometry carriers of my shape. And there are three types of geometry carriers. One of them is vertex, then edge, and then face. So vertex has a geometry of a point, edge is a trimmed curve, and face is a piece of a surface. So you see that these tolerance values are kind of small, and this basically means that I have a watertight solid. So OpenCascade modeling is unitless. You do not have any physical units associated with your geometry, but actually it's implicitly assumed that you are working with millimeters, and this basically means these tight tolerance values mean that you have a very small fraction of a millimeter over here, and that's perfectly fine. And big tolerances are kind of a problem. It's always a problem, so make sure that your tolerances are kind of good whenever you do something with OpenCascade. So now I am ready to go. I am ready to export this solid to a step file, and for that I'm going to use this stepwrite command. And here I need to pass a couple of arguments. The first one is a mode, because I can export my resulting solid into different entities of a step file. And actually, if I do not care much about this topic, then I just pass a, which means as is. This a basically means that if I have a solid object, then the outcome entity in a step file is going to be manifold solid brep. Then I pass a name of my shape, and finally I pass a file name, which is going to be demos, for example, and then, I don't know, test stp. Let's go like this. And you see I'm kind of done. So if I go to this destination folder, I see this test STP over here. What I can see inside is that, okay, I have my OpenCascade version 7.6, some other step entities, and actually here I would expect to find this manifold solid brep. So for solid object you would expect to have this entity, and actually here you see that it points to the 16th entity, which is a closed shell, and then closed shell is a container of advanced faces. So here you can notice that this set of entities, this set of types, which is used in a step format, it's kind of a reflection of all the types and all the data structures which we have in OpenCascade itself, because OpenCascade is sort of inspired by this step standard, and it's nicely compatible with it. So I think we are done here. So let's try finally to open up our step file in some commercial CAD package to see that we can easily communicate our modeling result with external world. So I'm going to use SolidWorks for this test. So let's try to import our shape here and to see what we are going to get. So here we go, we have our solid object in SolidWorks, and we can do whatever we want in SolidWorks as well. So you see, draw is a kind of very handy thing which you might want to have in your toolbox whenever you do some CAD processing, CAD analysis and prototyping things. And if you learn how to use draw, if you learn the basics of TCL syntax, it's going to pay off. It's going to be a useful thing in your armory of tools. As you may guess, draw is a very powerful and very big application in a sense that it contains tons of different TCL commands. So if you are looking for some reference, then you can go to the development side of OpenCascade, which is dev.opencascade.org, and then you go to the resources and here to online documentation. In the full online documentation section, you will find this user's guide section, and here you can go to draw test harness, and actually here you have this table of contents with many commands listed here. So basically these commands, they cover different facets, different aspects of the library, starting from very low level shape interrogation methods like curve and surface evaluation, and then you also have here all the modeling API and also things related to OCAF and visualization. So I would suppose you to give it a try to learn how to use this Pocket TCL language, because it's pretty simple language actually. It's not Python, it's not object oriented, and it works pretty well for daily automation scenarios. So I wish you good luck, I wish you good experiences with Draw, and see you in our upcoming lessons.